Now that we've studied ideal parallelism, let's try and understand what happens in a real machine. In a real machine, you have two processors. For example, if you have a dual core machine, P1 and P2, and if you have a computation graph such as the ones we've seen before, so let me draw one here over here, S1, S2, S3, S4, S5, S6. The graph shows you the ideal parallelism, but what's actually going to happen is these steps will have to be mapped onto the processors, the two processors over here, to run in a realistic way on a real machine. So let's provide some execution times over here. Let's say S1, S2, S3, S4, S5 all take 1 unit of time, and S6 takes 10. And based on what we've seen earlier, we can say that the work is the sum of the times, which is 15, and the critical path length comes through S6, which is 11, 1 and 10. Now let's imagine two possible schedules on this parallel machine. In one case, processor 1 could execute S1, processor 2 will be idle because nothing else can happen when S1 is executing. After that, processor 1 could pick up S2 and processor 2 could pick up S4, and then 1 could do S3, 2 could do S5, and then the only thing that remains is S6. It doesn't matter which one does it, let's say 1 does it. And the total time required over here, because S6 takes 10 units and you have 1, 1, 1, the parallel time for this schedule is 13 units. However, if you look a little more carefully at the graph, we could have done better. Over here, we ended up postponing S6 till the very end, which is not smart because S6 was the bottleneck in the computation graph. It takes the longest amount of time. So an alternate approach would be to again look at two processors, P1, P2, and again we have no choice. We have to do S1 to begin with, but now we can be smarter, and we said we ought to give priority to S6 because it takes the longest amount of time. So let's go ahead and do S6 first on processor 1, and that runs for 10 units. Now while S6 is running, processor 2 could pick up S2, it could pick up S3 or S4, it doesn't matter. Let's say it does S3, then it does S4 and S5. And all this work is overlapped with S6. So if we look at the parallel time over here, it is 11 units, which is much better than 13 units. And in fact, we know it's the best we can do because the critical path length is 11. So even if we had more processors, we could not do any better. So what we've seen is that for a given computation graph and a fixed number of processors, it could be 2, 3, 4, 10, 1,000, there can be different schedules of the same computation graph that result in different execution times. And this leads to some interesting ideas in how best to map your program on a parallel machine.